This is your presenter Asloob Mudassar, and I am presenting slide number 12A of the course on atomic and molecular physics. Today I shall be covering the following topics: orbital and spin magnetism, fine structure, orbital angular momentum, and orbital magnetic moment and their precession in applied magnetic field. Orbital and spin magnetism. Shell structure of an atom is explained further through the magnetic properties of an atom. That is, in order to investigate the magnetic properties of an atom, we apply external magnetic field to an atom and we see the behavior of the atom under the application of applied external magnetic field. There are some experiments that govern the magnetic properties of an atom, and one is the Einstein-de Haas effect. It deals with the measurement of the macroscopic magnetization and the gyromagnetic properties of solids. So you see that under this experiment we shall have the possibility to measure two main properties. One is the macroscopic magnetization and the second one is the gyromagnetic properties of the solids. Now the next experiment is the Stern-Gerlach experiment. It deals with the measurement of the directional quantization and the measurement of the magnetic moments of atoms in atomic beams. That is what will happen if we apply the external magnetic field, and what is the meaning of directional quantization and the magnetic moments of an atom. These will be investigated under the Stern and Gerlach experiment. The experiment leads to the observation of a fine structure in the optical spectra of the atoms. Fine structure means that we can resolve further in further detail. We can resolve those lines which we have not talked yet and which were unresolved by the theory that we have presented so far. Now we would be able to further resolve them under the heading of fine structure. So fine structure means that we would be able to see the detail of the further structure and the detailed structure of the lines of the spectral lines which we call as fine structure. In the spectra of alkali atoms, all the energy terms represented by the energy capital E with N and L, where L is not equal to 0, are split in two terms called doublets. So in the previous slides, in the previous lecture, we have seen that in the alkali metal atoms, where the energy of the levels depends upon both quantum numbers, two quantum number. One is the principal quantum number n and other is the orbital quantum number L. So those levels will split into two levels which we call as doublet levels. And the condition is that when L is not equal to 0, that level will not be split into two levels, that will remain as a single level. But all the other levels in which L is not, that is the orbital quantum number is not equal to 0, then there will be a further splitting of such levels which we call as doublets. This is what we have seen in the alkali metal atoms in the previous lecture. The doublets differs fundamentally from the lifting of orbital degeneracy. So you see that we have seen the lifting of orbital degeneracy in the previous lecture when we talked about the alkali atoms. And we see that the energy of the alkali metals depends upon the orbital quantum numbers, and the orbital degeneracy is lifted means that the energy is now that the energy will now depend upon the principal quantum number, and in addition to that one, the orbital quantum number of the atom. So that's why we call it as lifting of orbital degeneracy, which means that the energy is now going to depend, besides the principal quantum number, and it is going to depend upon the orbital quantum number L. So that's why we call it as the lifting of orbital degeneracy. This is what we have talked in greater detail in the while discussing the alkali metal atoms. Now consider D lines in the transition 3p to 3s from the sodium atom. So in the sodium atom, now we are going to consider this transition 3p to 3s or 3s to back to 3p. This is a sign, the double arrow sign, which means that this is a two-way transition, that you can make a transition from 3p to 3s and backward from 3s to 3p. With the sufficient spectral resolution, two lines D1 wavelength of 589.59 nanometer and D2 with a wavelength of 588.96 nanometer are observed. So under this transition, which is a 3p to 3s transition from the sodium atom, we can observe two wavelengths, D1 and D2, the wavelengths of which I have just mentioned. This pair of lines will be used to explain spectroscopic results. So you see that you have two lines in the spectrum, and if there are any other lines which are unknown, so with respect to these known wavelengths, we can also determine those unknown wavelengths. So this pair of lines will be used to explain spectroscopic results, because these can act as a reference lines for the spectroscopic data which is unknown. These lines are specially suitable for demonstration of basic concepts in atomic spectroscopy. So since these wavelengths are very useful and very popular in spectroscopic data, so these wavelengths will be very useful in the analysis of other unknown wavelengths. Spectrometer arrangement based on two sets of prisms for the spectral separation of two components D1 and D2 from the sodium D lamp is shown below. So you see that in this setup we have the sodium lamp. This sodium lamp, which is very filtered lamp, contains two wavelengths. One is called D1 and the other is called D2. So D1 and D2 are the two wavelengths that we can that are present in the sodium light, in the light from the sodium lamp, and we want to resolve them. For that one, we are using two sets of prisms. So you see that the light from the sodium lamp will pass through a slit. Slit provides a point source. A very narrow source is created at the center of the slit, and there is a lens on the right side of the slit which is located at a distance equal to the focal length of the lens. So this lens is called a collimating lens because it will generate a parallel wavefront after the light passes through it. So a parallel wavelength from the lens is generated in the, because it is a collimating lens, it will generate parallel wavelengths, and these parallel wavelengths will pass through two sets of prisms. These prisms are called these prisms are actually the dispersing elements. So what will happen? So what they will do is that they will slide to separate out D1 from D2. So the prism 1 will separate D1 line from D2 line, and the second prism will multiply this one, will further separate the D1 line from the D2 line, and the lens, which we call as a focusing lens, will focus the two parallel beams into two spots which will focus to be as D1 line and D2 line. So you see that the sodium lamp at the left mode on the left hand side is a sodium lamp, and it contains two wavelengths, and this setup, which we may call it as a spectroscopic as a spectrometer consisting of two sets of prisms, and these prisms are acting as a dispersive element separating the two wavelengths apart from each other, and then you can measure the two wavelengths D1 and D2 on the screen well separated from each other, because the separating power of these prisms is large, because these prisms have very large dispersing properties, and due to that one, the wavelengths D1 and D2 are separated out by the two sets of prisms, and they are well separated and being focused by a lens into two discrete point sources. So D1 and D2 are the two point sources, giving you a wavelength corresponding to D1 and D2. So you see that this spectrometer arrangement will help you to separate out or to separate out the two wavelengths present in the sodium source. Spectrometer arrangement based on the single prism for the observation of D1 and D2 wavelengths of the sodium D lines through absorption spectrometer. So you see that here we are using an absorption spectrometer, and you know that in this absorption spectrometer we have the xenon lamp, for example, xenon lamp providing you a broad band, a broad source of light, and it's passing through a lens. This is a focusing lens which will focus the xenon lamp source onto a single point source at the center of this slit. So the point source located at the center of this slit will diverge out in the form of spherical beam, and the spherical beam will be incident on the collimating lens, because the collimating lens is placed at a distance f equal to the focal length of the lens, and the distance between the slit and the collimating lens is the separation, and this separation is equal to the focal length of the lens. And after the collimating lens, the light will become a parallel wavefront. That is, a collimated beam is generated by the collimating lens. And this beam will pass through the prism. And the prism will, the function again, dispersing element, the prism will separate out different wavelengths present in the xenon light source. And the focusing lens will focus them out separately. So in the screen, I have shown a single point, but actually there are many such points over here. Many focusing points are located on the screen. For example, in the previous case, you could see that there will only two spots, two focusing points over here, because only two wavelengths are present. But since the xenon contains a large number of wavelengths, so this is a single point source, but there are actually many point sources which have been focused by the focusing lens. So many point sources are located on the screen, in each indicating a separate wavelength. So you see that a continuous spectrum is obtained on the screen. Now what we are going to do is that we are going to place a chamber that contains sodium vapors. So when the sodium vapors are placed over here, what will happen? The sodium vapors will absorb the lights corresponding to the D1 line and D2 line, because these wavelengths will be absorbed by the sodium vapors and will be re-emitted in other directions, not necessarily to be in the direction of the beam which is going out of the collimating lens. It might be possible that a small portion is emitted in that direction, but the majority of the light will be transmitted, or will be delivered, will be emitted by these sodium vapors in other directions. So these D1 and D2 lines will be missing in the collimating beams. So when you will look at the spectrum at the screen, you will see that there will be two black lines over here. It means that some data has not reached at that 2 points due to the absorption of the sodium D1 and D2 lines. So corresponding to the D1 and D2 lines, you will see that there is a black region corresponding to D1 line, and there is a black region corresponding to D2 line, and at the other positions, the full spectrum is available. So this is called the absorption spectroscopy. In the absence of vapors, a continuous spectrum is observed on the screen. When sodium vapors are present in the path of the beam, the sodium D lines are absorbed and black bands are seen on the continuous spectrum. That is, two black lines, two black bands will be seen corresponding to two D lines of the sodium structure, that is D1 and D2 lines. The setup may be regarded as absorption spectroscopy. So you see that in this absorption spectroscopy, there will be a continuous spectrum on the screen when the sodium vapors are not present, but when the sodium vapors are present, then we can observe in this continuous spectrum two black spots or two black bands corresponding to D1 and D2 lines of the sodium vapors, because the sodium vapors have absorbed those lines from the light coming out from the xenon lamp and have scattered them away from the main stream of the from the main stream of this optical system, and they will not contributing at the screen and will appear as two black bands. Now we are going to explain explanation of doublets. The following three modifications are required in atomic physics theory presented so far. So you see that up to the lecture number 11, the theory that I have presented up to lecture number 11, now there is need to make some addition to that theory. So the following three modifications are required in the atomic physics theory presented so far. Number one is that a magnetic moment mu L is associated with the orbital angular momentum L, or equivalently with the orbital quantum number L. So the main thing is that the magnetic moment mu L is associated with orbital angular momentum L. You see that so far up to lecture number 11, we have discussed the orbital quantum number L. Now here we are talking about another quantity, which is the magnetic moment, or more precisely you can say that it is the orbital magnetic moment of the atom, which is associated with the orbital angular momentum L of the atom. The second point is that an electron has a spin angular momentum S. So this is a new addition, that a spin angular momentum exists associated with the electron, and a quantity which is also associated with the spin angular momentum is the spin magnetic moment. So this is mu s is the spin magnetic moment. So very simply, we have the orbital angular momentum, and associated to that one we have orbital magnetic moment mu L. And there is another quantity that new quantity that we are talking about is the spin angular momentum, and a quantity which is associated with the spin angular momentum is the spin magnetic moment. So we have L vector associated with that one, we have a mu L vector, and similarly we have S vector, and associated to S vector we have the mu S vector. That is the orbital, that is the magnetic momenta, and the associated quantity which is the magnetic momentum. Mu S and mu L interact with each other. Both can be parallel or anti-parallel to each other and have slight different binding energies in the two modes. This leads to fine structure of the spectrum. So you see that here the word fine structure is very important, and fine structure is responsible for the splitting of the doublets, which we call the doublets. So doublets mean two lines, and this is associated for the case of a single electron. If the valence electron is a single electron, then we have the doublet lines. And as said earlier, it is necessary that L should not be equal to 0. Okay, doublets lines. And when we have the doublets lines, this is called fine structure. And the source of this doublet line is the interaction between the mu S and the mu L. And you know that mu S is due to the spin angular momentum, and mu L is due to the orbital angular momentum. So you see that these two quantities, that is mu S and mu L, will interact with each other, maybe in the parallel configuration or in the anti-parallel configuration, and will produce a quantity which we call as the due to these one, their energies could be different. That is, in the parallel mode, the energies could be different from those of the anti-parallel mode. And due to difference of energies, the two lines appear, which we call as the doublet lines. And the separation of the doublets line, or the resolving of, or the resolution of these doublets line, is called the fine structure of the spectrum. So I now hope that the word fine structure will now be clear. And fine structure is associated completely with the doublets. And the doublets will only appear when we are talking about that the valence electron is a single electron. So when there is a single electron present, then we can say that doublets will appear, and we can observe the fine structure in the spectrum. That is, we can observe the two lines. Doublet means two lines. So you see that we are familiar with the orbital angular momentum L, but we have said that there is a quantity mu L associated with L, which we call it as magnetic orbital magnetic moment. So now we are going to discuss what is orbital magnetic moment. So that's why the heading is about mu L, that is orbital magnetic moment. This is a vector quantity, like the orbital angular momentum is a vector quantity. An electron being in motion acts as a circular electric current loop and generates a magnetic dipole field according to electrodynamics with the magnetic dipole moment mu L. So you see that here the word mu L appears. It is associated when we are talking about that the electron revolving around the nucleus appears as a circular electric current loop, and this current loop, due to this current loop, a magnetic dipole is generated according to the rules of the electrodynamics. And to that one, to the magnetic dipole, a quantity is associated which we call as magnetic dipole moment, represented as mu L. The magnetic dipole moment of a conducting loop is simply given by mu is equal to current times into area. I is the current of the current loop, and A is the area of the loop. So A is the vector area of the current loop of the electron, and I is actually the current that we can measure flowing in the current loop. This is completely a classical description, and mu is the quantity which is associated to that one. A current in a loop of area A will produce a magnetic dipole moment mu, which is given by equation number 12.1. So mu is equal to I times into A. This is the classical definition of the magnetic dipole moment. Where capital A in the form of a vector is the vector area, and it has a direction perpendicular to the plane of the conducting loop with the magnitude, and the magnitude of this vector area A is equal to the area of the loop. And you know that if the loop has a radius r, then the area of the loop is given by pi r square, and then the area of this vector A will be equal to pi r square, and it has a direction which is perpendicular to the direction of the current loop according to the right hand rule. So you need to curve your fingers in the direction of the flow of the current in the loop, and the thumb will give you the direction of the direction of the vector area A. If the magnetic dipole moment is placed in a homogeneous magnetic field B, the dipole will be subject to torque tau. Now you see that now we are talking about the external magnetic field B. And this magnetic moment mu is actually an internal concept, that is, it is associated with the motion of the electron in a circular loop. And so it generates orbital angular momentum L, and to that one there is an associated quantity which is called as the magnetic moment. So when this atom is placed in an external magnetic field capital B, then of course then the dipole moment of the electron, then the dipole moment of the electron will experience a torque, and this torque is given by tau is equal to mu cross B. And the magnitude of this one is tau mod is equal to mu b sine of alpha, where alpha is the angle between the vector mu and the vector b. So you can see over here that this is the current loop. The current is entering into the current loop, and you see that the current is flowing in the current loop. Here I have shown the current loop in the form of a rectangular loop, and then of course the current will exit the loop. So the current will enter into the loop, it will go through the complete loop, and then will exit the loop. And you see that I have shown a magnets with polarity N polarity and S. And you can see that the direction of the magnetic field, that is the external magnetic field, is shown as a capital B, and these long arrows shows the direction of the external magnetic field. And you can see that this n vector is actually a vector in the direction of the vector area A, that is, it is perpendicular to the plane of this loop. So this n vector is actually a vector which is perpendicular to the loop, and it has and n makes and makes and the vector n makes an angle alpha with the external magnetic field B. So you can also assume that if atoms are present over here, the atoms have circular loops over there, tiny circular loops, and if you apply the external magnetic field like the one I have shown, then of course the electrons in the loop, the magnetic moments will experience a torque, and this torque is given by tau is equal to mu cross B, and the magnitude of this torque is mu B sine of alpha. So this n here I am showing n as a unit vector, but in the figure I have shown n as a complete vector. So this n hat is a unit vector normal to the plane of the current loop with the sense defined by the right hand rule on the direction of current. So you need to apply the right hand rule in the direction of the current of the loop, and n hat will give you the vector, you will give you the unit vector perpendicular to that loop, and the vector n is the vector area. And here you can also represent, we can also represent this vector area with vector area capital A. So capital area A that I have shown over here, this capital area A is actually the same as capital area as vector n, because vector n is the same vector as the capital vector A, or the vector area A. So n vector is the vector area, the magnitude of which gives you the area of the loop. Mu is parallel to n. So this is the condition. You see that mu is parallel to n. I have not shown the direction of mu, but I shall show that one later on in the next slides. And alpha is the angle between the normal to the plane of the loop and the magnetic field. So you can see that the alpha has been indicated in the figure, that it is an angle between the vector n and the vector b, where vector b is the external magnetic field that we are going to apply to the atoms, and n vector is the vector which is perpendicular to the loop of the electron loop, or the current loop of the electron. Now, here we are saying that our dipole moment over orbital magnetic moment of the electron will be parallel to the loop, will be parallel to the vector n, that is, it is perpendicular to the vector n. This is what we are going to see in detail in the next slides. The magnetic potential energy, which we call as V with a subscript mag. V mag mean that this is the potential energy due to the magnetic field. So the magnetic potential energy V mag of the dipole is V mag is equal to the integral from pi by 2 to alpha. And you see that tau d alpha will provide you, if you multiply tau with d alpha and integrate from pi by 2 to any angle alpha, this will give you the magnetic potential energy of the dipole, and you can substitute the value of this one, that is the value of tau. So mu b can be taken out of that one, and sine alpha is over here under the integral. And if you integrate this one, you will get minus cos of alpha, and the integration will give you from minus mu b cos of alpha. Or simply you can say that it is minus mu times dot product of a mu dot product of a mu and b, or mu dot b. So this is the dot product between the two vector quantities, which is one is the orbital magnetic moment of the atom, and the second one is the external magnetic field applied to the atom. And V mag is the energy, is the potential energy stored in that in that dipole of the atom. And you see that here why we are going to integrate from pi by 2. Pi by 2 is the orientation at which the V mag is maximum, and we are going to integrate to any value alpha. And you know that the magnitude of tau that we have used is mu b sine of alpha. So now we are going to calculate the magnetic potential energy stored in the atom, which will be V mag, and this is what is equal to minus mu time mu dot B, as shown in equation number 4. Now there are two definitions of mu. One is mu is equal to mod of tau divided by B sine alpha, which this definition is what we have obtained from equation number 3, that is mu is equal to magnitude of tau divided by b sine alpha. This is one definition of a mu. And the second definition of a mu can be obtained from equation number 4, that is mu is equal to minus v mag over b cos of alpha. So these are the two definitions of the magnetic dipole moment of the electron or of the atom. And remember, here we are particularly emphasizing on the single valence electron in this chapter, because we are talking about the doublet theory, and doublet theory arises when there is only a single valence electron in the atom. So there are two definitions that I have shown in equation number 5 and equation number 6. In atomic and nuclear physics, the definition of mu in terms of tau is used. That is, the definition given in equation number 5 is mostly used. Or the more general definition that we have pointed out earlier is tau is equal to mu cross V. And the equation number 5 was derived from that. So I am rewriting that tau is equal to mu cross V. So I am multiplying this with mu naught and dividing by it with mu naught. You see that I have shown mu naught in the red color. So mu naught is multiplying to mu, and B is being divided by mu naught. So B divided by mu naught will give you capital H. And then we have mu naught times mu cross product with capital H. So capital H is actually the magnetic field and B is the magnetic induction. So this mu naught mu can be represented as mu prime. And here the value of a mu naught is equal to 4 pi into 10 to the power minus 7 volt second over ampere meter. To calculate the magnetic dipole moment mu of the electron revolving around the nucleus and acting as a current carrying loop, we use this form, that is I, that is the current flowing in the current carrying loop will be is equal to Q over T, where Q represents the charge of the electron. So Q can be replaced by minus E, and T, which is the time period of one oscillations of the charge around that is the time, capital time is the time taken by one, that is a time taken by the electron to complete one revolution, or time period. T is equal to pi over omega. And here you can write that current I flowing in the loop, in the current loop or in the electron loop, can be given as I is equal to minus E omega over 2 pi, as shown in equation number 8, where omega is the angular frequency of the electron. and capital T is the time period of for one oscillation, and T is equal to 2 pi over omega. So in the figure you can see that the electron shown in red dot and the center of the nucleus is shown through which the orbital angular momentum vector L shown perpendicular to that one, and this electron is moving with the velocity v is equal to r omega, is revolving in this current loop, is revolving in this loop. And you can see that there are two main quantities that I want to show. One is the orbital angular momentum. So you see that you can see that when electron revolves around the nucleus, a current loop is formed, and the vector L will be perpendicular to that current loop, and this angular momentum L is shown. And there is another quantity which is mu, which is the magnetic moment, is also shown, is also related to the vector L through this relationship, that mu is equal to minus E over m times the angular momentum vector L. But there is a negative sign over here. So due to that one, the mu vector has a direction opposite to that of the direction of the angular momentum L. So the orbital magnetic moment mu of the electron has a direction opposite to that of the direction of the angular momentum vector L of the electron. Now I shall explain why this value is equal to minus E over 2m times L vector. This is what I am going to explain. But here you must remember that the vector, that is the magnetic moment mu of the this magnetic moment is actually the orbital magnetic moment. If you want, you can place a subscript L over here. So this is the orbital magnetic moment of the electron, and this vector L is actually the angular momentum, orbital angular momentum of the electron. So these quantities are oppositely directed to each other. Now the vector mu I wanted to calculate, mu is equal to current into I, current in the loop multiplied by the scalar area. And you can see that the current from the previous slide we have calculated that the current is minus E omega over 2 pi, and the area of this loop is pi r square. So simplifying this result, I have minus half E omega r square as shown in equation number 9. So mu is equal to minus half E omega r square. The magnitude of the orbital angular momentum L is given by, you know that L is equal to m naught V cross R. So this is the classical definition. And if you take the magnitude of the vector L, you have m naught VR. Otherwise, the definition is R cross P or R cross V. So this is the definition of the vectorial form of the angular momentum. But here I am talking about the magnitude of the angular momentum. So the magnitude of the angular momentum of the electron is equal to m naught into V into R. So here you can substitute that V is equal to R omega, and then the final result is m naught omega R square. So from here you can solve this equation for the value of omega r square. So omega r square will be equal to the absolute value of vector L divided by m naught, or the magnitude of the vector L divided by m naught, as shown in equation number 11. So this omega r square can be substituted in equation number 9, and then you can find out the relationship for the orbital magnetic moment. So using the value of equation number 11, that is the using value of omega r square from equation number 11 into equation number 9, you can get the value of magnetic moment mu, which is shown in equation number 12. So the magnetic dipole, so the orbital magnetic dipole moment of the electron is equal to minus E over 2m naught into magnitude of the orbital angular momentum. And in the vectorial form, you can write this definition as shown in equation number 13, that is mu L in vectorial form is equal to minus E over 2m naught multiplied by the orbital angular momentum in vectorial form. So equation number 12 gives you the magnitude form definition, and equation number 13 gives you the definition of the orbital angular momentum of the electron in vectorial form. So you see that we have now two vectors, two quantities which are completely known to us. One is the orbital angular momentum of the electron, both in magnitude and in vectorial form. This quantity is known, and since this quantity is linked with mu L, so the orbital magnetic moment of the electron or of the atom is also known. So these two quantities are known to us. And one more important thing is that these two quantities are directed opposite to each other. And one more thing is that the directions of L, since is perpendicular to the current loop, so the direction of mu is also perpendicular to the current loop. But mu and L are directed opposite to each other. Now you see that from this definition, you can directly say that the proportionality mu L is directly proportional to L. That is, the orbital magnetic moment of the electron is directly proportional to the angular momentum of the electron. So this proportionality is known as the magnetomechanical parallelism, because later we shall see that it has an analog of the mechanical gyroscope, so that is why we call it as a magnetomechanical parallelism. That is, it is a parallel to the mechanical gyroscope in principle, which we shall see shortly. So this proportionality, which is mu L is proportional to L, is known as the magnetomechanical parallelism. So now we are going to define another quantity, but for that one, we choose that the magnitude of the orbital angular momentum is equal to 1 h bar. You know that in the Bohr's, while discussing the Bohr theory, we have given one statement that the angular momentum will take only values which are equal to the integral multiple of some of the principal quantum number. There we stated. But you know that there we have you can go through the Bohr theory in some of the previous slides, and here we are choosing that the magnitude of the orbital angular momentum is equal to 1 h bar, which is applicable to the first Bohr model, in hydrogen atom. When we're talking about the old Bohr model, and then the resulting mu in magnitude form is called the Bohr magneton, denoted by mu b. You know that this angular momentum L has the minimum value that it has is 1 h bar. This is the minimum possible value for the orbital angular momentum to have a value. You know that we shall see later, we shall also see this later very clearly, that the orbital angular momentum is also linked with the orbital quantum number L. This is what we shall see shortly, but here we are going to take the minimum value of the magnitude of the orbital angular momentum, which is 1 h bar. So if you choose this value, which is equal to 1 h bar, so you see that in equation number 12 you can put the value of this minimum value of this orbital angular momentum. The minimum value of this one is 1 h bar. If you put this value equal to 1 h bar, what will happen? We give it a different name, which is called mu b, Bohr magneton. So here I have substituted the value equal to 1 h bar, and then you can see that the value is, all these are constants. Charge of the electron, h bar, Planck's constant, reduced Planck's constant, m naught is the mass of the electron. All these quantities are known, and if you substitute or plug in these values over here, you can find the value of the Bohr magneton to be equal to 9.274078 into 10 to the power minus 24 ampere meter square. So this is definition of the Bohr magneton, and it is related with the, you know that Bohr magneton is the same as the orbital angular momentum of the electron, but only when the orbital angular momentum has the minimum possible value, then this mu L is called Bohr magneton. So we have defined Bohr magneton because there are some quantities which we shall represent in the form of the Bohr magneton. That's why we have given its definition over here by using the minimum value of the orbital angular momentum. From equation number 12, we have mu L is equal to E over 2 m naught into magnitude of orbital angular momentum. And you know that in one of the previous lectures, we have seen that this L mod is equal to L, it is equal to the square root of L into L plus 1 times H bar. This is what we have seen. And you know that if you put the value of L, here L, these L are the quantum numbers. So if you put the value of L is equal to 0, what will you get? You will get that the square root of 1, and the square root of 1 is equal to 1. So that will equal to 1 h bar. So you see that when L is equal to 0, that is the orbital quantum number, L is equal to 0, then the magnitude of the L vector, then the magnitude of the orbital quantum of the orbital magnetic moment, sorry, the orbital angular momentum will be equal to 1 h bar. So that's why this we have chosen 1 h bar, because this corresponds to the value of the quantum number equal to L is equal to 0. So if you put L is equal to 0, then you will see that this L mod will become equal to 1 h bar. And the value of this L mod, that is the magnitude of the angular momentum, has been defined earlier to be equal to the square root of L into L plus 1 times h bar, where L is the quantum number. So you can now separate out these terms, E h bar over 2 m naught, and you can keep the square root terms separate. And this E h bar over 2 m naught is nothing but the Bohr magneton, which we have defined in equation number 14. So that's why mu L can be defined as mu B times square root of L into L plus 1. So you see that we have defined over angular momentum, over Bohr, over orbital angular uh, magnetic moment. This is the orbital magnetic moment. So we have defined the orbital magnetic moment in terms of the Bohr magneton multiplied by the square root of L into L plus 1, where these small l are actually the quantum numbers. That's why we have used a subscript with mu as a small l, because this will be linked finally with the angular momentum quantum numbers. So equation number 15 is a very important results. Now let's consider further details, because there are some other quantities that we are using. You know that these are the quantities that we are preparing for the analysis of the spectrum. Finally, these quantities will be used for the analysis of the spectrum that we obtain. So in order, so that's why we are defining these quantities, and we are creating and we are developing new quantities over here. One is the quantity that we have developed is mu L, which is the orbital magnetic moment of the electron, is related with the Bohr magneton multiplied by the square root of L into L plus 1. In the vectorial form, this definition is over here that we have discussed in equation number 13. So this is what I have taken from equation number 13. In the vectorial form, we have this definition. Again, I can introduce the E h bar over 2 m naught over here, so that I can introduce the Bohr magneton. And this L vector, L in vectorial form divided by h bar, will remain as such over here. And then we have mu B Bohr magneton into L vector over h bar. And you see that here GL, I have introduced a new quantity GL over here. At present, in equation number 12.15a, GL is equal to 1. Later on, we shall see what is the significance of GL. But you see that here we have introduced GL as a parameter. And in equation number 12.15a, GL has a value which is equal to 1. And we have now final result that mu L in vectorial form is equal to minus GL times mu P times the angular momentum vector divided by H bar. So you see that we have written a more comprehensive definition of the orbital magnetic moment in terms of these quantities. Now it may not be necessary that GL is always equal to 1. When we introduced GL in equation number 15a, we said that GL is equal to 1. That's now final. But later we shall see that GL may have different values other than 1. So that's why we have kept GL over here in the definition given by equation number 16. So this is another quantity that will be helpful in the analysis of the spectrum or in the analysis of spectroscopy. So you see that quantity defined in equation number 15, defined in equation number 16 are very important for us. Now you see that from equation number 16, you can solve equation number 16 for the definition of the parameter GL, which is shown in equation number 17. So GL is equal to, I have dropped the negative sign because that is not very much important. GL is equal to mu L divided by mu B, and in the denominator I have the vector L divided by H bar. You know that mu L is measured in mu B, and the vector L, which is the orbital angular momentum, is measured in terms of H bar. So that's why I have written this definition in the following form. So GL is a measure of the ratio of the orbital magnetic moment, mu L orbital magnetic moment in mu B to the orbital angular momentum in H bar. So GL is nothing but it is the ratio of the measurement of the mu L in terms of mu B and L in terms of H bar. So you can measure mu L very easily provided you specify the orbital angular momentum L in terms of Bohr magneton, and you specify the angular momentum of the atom or the electron in terms of H bar. And if you compute this ratio, you will get the value of GL. So GL was introduced by Landé in the presence of the spin orbit coupling. So you see that so far I have not talked about the spin orbit coupling because so far I have not introduced the spin quantum number or the spin magnetic or the spin angular momentum. I have not introduced this spin angular momentum. So I cannot talk about yet spin orbit coupling. But just remember that Landé introduced GL by getting through the concept of spin orbit coupling. I shall be explaining spin orbit coupling maybe in the next lecture. But here I am concentrating only on the orbital thing. That is, I am concentrating on the orbital angular momentum and on the orbital magnetic moment of the atom or the electron. So I shall be talking about the spin angular momentum or the spin magnetic moment or the spin quantum number in the next slide. I mean in the next lecture. So the maximum component of mu L in the z direction is calculated as. Now what is the z direction? If you have atoms, if you apply the magnetic field to those atoms, the direction of the magnetic field is regarded as the direction of the z direction. So the z direction or the magnetic field direction, both are the same things. So whenever I am referring the z direction, it means that I am referring the direction of the magnetic field, or when I refer to the direction of the magnetic field, that is the direction of the external magnetic field, it means that I am talking about the z direction. Now you see that we can apply the magnetic field over here. And when we apply the magnetic field to a current loop, this current loop could be a circular current loop in the when an electron is revolving. You can consider this as a circular current loop, and perpendicular to that current loop, you have the orbital angular momentum, and reverse to that one in opposite direction, you have the magnetic moment. As you can see, that the direction of the magnetic orbital magnetic moment is opposite to that of the angular momentum of the electron. So you see that when you apply the magnetic field in a different direction, then what will happen? The orbital angular momentum L of the electron starts its precessional motion about the magnetic field. Suppose that you apply magnetic field and the magnetic field lines make an angle alpha with the vector with the orbital angular momentum L of the electron. Then what will happen if the angle is fixed? Suppose that the angle alpha is fixed. Then the vector L starts precessional motion about the magnetic field, and it will have a component in the direction of the magnetic field. So the precessional motion of the vector L about the magnetic field will start, and due to that precessional motion, there will be a component of the angular momentum L, which we call as the Z component, in the direction of the magnetic field. So the maximum component of mu L in the Z direction is calculated from. So you see that I have the definition of a mu L, the vectorial definition as shown in equation number 16. So you can take the Z component of that one, which I have shown over here. So Z component on both sides, Z component of the angular momentum on the right hand side, and Z component of the magnetic moment of the orbital magnetic moment on the left hand side. And you know that Lz, which will be the Z component of the angular momentum, it has a value which is equal to ml into h bar. This is also what we have discussed earlier. In the earlier lectures, we have discussed that the Lz has a value which is equal to ml into h bar. And you know that their ml was defined as the orbital magnetic quantum number of the electron. So ml is the orbital magnetic quantum number of the electron multiplied by the h bar. This is the value of the Lz. And you know that you can cancel out h bar over here. And I have written on the left hand side, I have written the quantity mu as mu with the subscript L and Z, because now this is a scalar quantity, and I am talking about the Z component of the mu L. That is the component of mu L in the direction of the magnetic field. So this is the component of mu L in the direction of the magnetic field. And you know that mu Lz now depends upon again three quantities minus GL times Bohr magneton times orbital magnetic quantum number of the electron. Now, if you want to calculate what is the maximum value of this quantity, you can take the maximum on both sides. You know that the maximum value of the orbital magnetic quantum number is equal to L, which is the orbital quantum number. So this is the orbital quantum number L. You know that ml is the orbital magnetic quantum number, and its maximum value is equal to the orbital quantum number L. So we have on the left hand side mu Lz maximum is equal to minus GL times mu d times L, where L is the orbital quantum number. You see that you can differentiate the quantum numbers L from its magnitude, from the magnitude of the orbital angular momentum. Is that whenever I shall write the angular momentum, that will be written either in the vectorial form as shown in equation number 16. Orbital angular momentum is shown in vectorial form, or I can show the orbital angular momentum in the magnitude form. And whenever I shall show the magnitude form, it will be shown as shown in equation number 12. But if I show a vector L, if I show a quantity L that is neither in the form of a vector or nor in the form of a magnitude, then you will assume that that quantity is the quantum number. So you can discriminate the quantum numbers from the corresponding quantities. So here L in equation number 18 is actually the quantum number, orbital quantum number. So here L is the orbital quantum number. So next we discuss what happens to the magnetic dipole moment of an atom when it is placed in the applied magnetic field. So this is what we are going to discuss, very important thing. We are going to place an atom having a magnetic dipole moment mu L in the applied in the external magnetic field, and we want to see what will happen to such an atom. One thing is the precession and orientation in the magnetic field. That is, when you place an atom in the presence of the external magnetic field, the orbital angular momentum of the electron, which is always perpendicular to the current loop formed by the electron, that angular momentum will start its precessional motion about the applied magnetic field. So here we define B as the magnetic flux density applied to the orbital magnetic moment mu L. Mu L will be aligned parallel to B, as in this orientation the magnetic potential energy, which is given by V mag, which is equal to minus mu B cos of alpha, is minimized. You know that when mu L is in the direction of B, then alpha will be equal to 0 and cos alpha will be equal to 1, and you have this V mag, that is the magnetic potential energy, will be equal to minus mu B, and this minus sign indicates that it has the minimum possible value. So the potential energy, magnetic potential energy, will have its minimum possible value when the orbital magnetic moment of the electron will be aligned in the direction of the applied magnetic field. So that is the case when the atom will have its minimum energy. And under the other condition, when it is not aligned, the magnetic moment, the magnetic angular momentum of the electron and the magnetic moment of the electron, both these quantities will start precessional motion about the magnetic field B. You know that both these quantities, that is L vector and mu L vector, they are perpendicular to the current loop formed by the electron, but they are oppositely directed. One will precess its precessional motion about the magnetic field, and the other quantity will precess its will carry out its precessional motion about the minus magnetic field. Under the application of the applied magnetic field, the electrons in their orbits behave like mechanical gyros and carry out the usual precessional motion about the magnetic field. So here in this figure, you will see that this is the current loop in which the electron is revolving in the current loop, and in the center of the current loop there is the nucleus. The electron shown in red is revolving around the nucleus in the form of a current loop, and this current loop, in the absence of the magnetic field, is shown can take any orientation. And you can see that there are two quantities which are perpendicular to this current loop. One is the orbital angular momentum of the electron, and the other is the orbital magnetic moment of the electron. These two quantities are perpendicular to the current loop, but they are mutually at 180 degree directed to each other. And you know that this electron then will, this orbital angular momentum will carry out its precessional motion about the magnetic field. precessional motion mean like this. The arrows that I am showing over here, this will show you the precessional motion about the magnetic field. So L will carry a precessional motion about the magnetic field like that of the gyros, mechanical gyros. And you know that this arrow is shown. It shows that this L vector will carry out a precessional magnetic field, a precessional motion about the magnetic field, which we simply called as precessional motion, or we say that L precesses about the magnetic field when an external magnetic field is applied. And you know that in this diagram, I have shown two other quantities. One is Lz. Lz is the z component of the vector L along the b direction or along the z direction. And I have shown another quantity mu Lz. This mu Lz is actually the projection of a mu L on the z axis or on the z or on the b direction. And you know that b direction or the z direction are the same things. So now there is a concept of directional quantization. Only Lz and mu Lz can be observed. Z is the direction of B. So you see that there are two quantities that we can measure physically. One is the Lz component and the other is the Z component of mu L. These two quantities can be observed, can be measured in different experiments. And these two quantities are quantized. That is, they have a specific direction and they have specific magnitudes also. You see that I have shown you one component of the vector L, which is the Z component. The other two components of the vector L will be Lx component and Ly component. These two components will be located on the current loop. So Lx component and Ly component are located on the current loop. When the electron revolves around the current loop, their magnitudes varies from minimum to maximum, and then maximum to minimum, and then again to zero. So during the motion of the electron, the Lx component and the Ly component are averages out to zero. So these two components will average out to zero. And only one component, which is the Lz component, the component in the direction of the magnetic field will survive, and we can measure this component. Similarly, we can measure this component mu Lz. So you see that here in this diagram, I am going to explain in much greater detail. You have the applied magnetic field, which is shown, and this is the current loop of the electron over here. Electron is revolving in its current loop, and the perpendicular direction to this current loop, and the vector L is shown. You can see that the vector L, which is perpendicular to this current loop, is shown, which makes an angle alpha with the direction of B. And you see that this red line over here is actually parallel to the direction of the magnetic field, and L vector L makes an angle alpha with the line parallel to the magnetic field. So you see that when this electron will move in its loop, the vector L will carry out a precessional motion. This precessional motion is shown in the form of a current, is formed in the form of a loop over here. So this upper loop is actually the precessional motion of the vector L, that is the orbital magnetic moment, orbital angular momentum of the electron about the magnetic field B. This is the precessional motion. So you see that if you take a projection of the vector L on parallel to the magnetic field B, you will get this quantity L mod sine of alpha, which will give you the radius of the upper loop about upper loop, which indicates the precessional motion of the angular momentum L. So after some time, this angular momentum L will take a new position, and its angular momentum will be equal to L plus delta L. And you know that delta L is also shown on the upper loop. So this delta L will show a projection at the center of this loop to be equal to delta phi. So the arc of delta L will will project an angle delta phi at the center of this precessional loop, which gives you the precessional motion of the vector L, and the radius of that precessional loop is L mod into sine of alpha, and delta L will project an angle delta phi, and omega phi and omega p is the angular frequency, or the p stand for the precessional frequency, precessional angular frequency of the vector L about the vector B. This is the precessional motion of the vector L about the vector B. Now let's try to do some mathematics so that we can find out some relationships. Alpha is the angle between the direction of B and L, as obvious from this diagram. Vector diagram for the calculation of the precession frequency omega p of a gyroscope with angular momentum L and the magnetic moment mu. You see that I have not shown the magnetic moment mu over here or in this diagram, and of course the magnetic moment mu is oppositely directed to the vector L. So as vector L precesses, as shown by the upper loop, the magnetic moment mu will precess also about the negative v direction in a loop below the loop of the current loop, which I have not shown. So tau produces a change in angular momentum delta L. So you see that this change in the magnetic field in the angular momentum delta L is due to tau, because we have placed the atom in the presence of the magnetic field, and the magnetic dipole moment of the electron will experience a torque, and the torque will produce a change in the angular momentum delta L, and the delta L will start its precessional motion due to the torque tau, causing L to precess or to carry out the precessional motion about the z direction or the applied magnetic field B. So delta phi is the angle of precession corresponding to the change in angular momentum delta L. So delta phi is linked with the delta L. So both are actually directly linked with each other. So when delta L will increase, delta phi will also increase, and vice versa. Now by definition of tau is equal to the rate of change of delta L. So the absolute value of tau is equal to delta L mod divided by delta t, and delta L mod is equal to, from this diagram you can see that delta L can be calculated as delta L is equal to the radius of this loop. Delta L mod is equal to the radius of this loop, which is equal to this quantity multiplied by the angle delta phi. So we have given the magnitude of delta L over here, that delta L is equal to the radius, which is equal to L mod into sine of alpha multiplied by the angle phi. So I have delta phi over delta t over here. So delta phi over delta t is nothing but omega p, which is the precessional angular frequency of the electron. So from here you can get the value of omega p as omega p is equal to value of the torque, or the magnitude of the torque divided by the magnitude of the angular momentum multiplied by sine alpha. You can substitute the value of tau over here from equation number 12. This is equation number 12. You see that here you can substitute, you can take out the value of mod of L from this equation, from equation number 12, and you can substitute that one over here. So omega L. So from equation number 12, we have tau, magnitude of tau is equal to mu L times B times alpha. And we are using the value of mu L over here from equation number 12, which I have shown you that mu L is equal to E into mod of L divided over 2 m naught. So we can eliminate tau mod from these two equations. So you have equation number 19, equation number 20. You can substitute the value of tau mod from equation number 20 into equation number 19. And then you can find out an expression for omega p, which is equal to omega p is equal to EB over 2 m naught. You see that the value of the precession frequency of the current loop or the precessional frequency of the orbital angular momentum about the magnetic field is given by this relationship, and it depends upon the value of B. So the greater the value of B, that is the greater the value of the applied magnetic field, the greater will be the precessional motion of the angular momentum about the positive B direction, or the precessional motion of the orbital magnetic moment of the electron about the minus or the negative B direction. Let us extend this definition to atomic gyroscope using equation number 16. So omega L is equal to, you know that this is what we have derived this equation from equation number 16. You will see this is equation number 16. So from that equation you have omega L is equal to tau mod over L mod into sine of alpha, and tau, the value of the tau magnitude or the magnitude of the torque is equal to mu L into B into sine of alpha. And we have by definition that omega L is that we have the denominator, we have the mod of an orbital angular momentum multiplied by sine of alpha. This is what we have obtained from the previous definition, that is from the definition of omega p. You can also represent omega p by omega L. So omega p is the precessional motion, and in atomic physics this precessional motion is represented by omega L, which we call as the Larmor frequency. So this omega L is actually the same thing as omega p, but in atomic physics we represent omega p as omega L, but the definition is the same. That is the mod of tau divided by the absolute value of L into sine of alpha. So you can put the value of mod of tau, which is mu L into sine of alpha, and the value of mu L taken from previous equation, that is from equation number 16, is GL into mu B into L mod over H bar. This is the value of mu L, which I have taken from equation number 16, and then you can have mod of B over here. Sine alpha terms will cancel out from the numerator and the denominator. Now you can arrange these terms, especially in the green terms. You can notice that the terms in green color, this is GL into mu B over H bar, and I have separated B from here because L mod will also be cancelled out. So on the right hand side I have gamma into B, because gamma is the same quantity shown in green, and on the left hand side I have the Larmor frequency. So I can find out gamma, that gamma is equal to GL into mu B over H bar. This gamma is known as the gyromagnetic ratio. It is equal to the precession frequency when B is equal to 1 Tesla. So you see that if you put the value of B is equal to 1 Tesla in equation number 22, you will see that omega L becomes equal to this quantity gamma. So gamma is actually the gyromagnetic ratio, and it becomes equal to the precession frequency or Larmor frequency when the applied magnetic field is equal to 1 Tesla. So that's why gamma is very important. So the Larmor frequency omega L is independent of the angle alpha. You see that omega L, the expression of the omega L given by equation number 22 is independent of the angle alpha. So it does not depend upon the angle alpha. So we can say that the Larmor frequency omega L is independent of the angle alpha. Now I am carrying out this discussion further. You know that I have shown you this L mod is equal to 1 H bar I have shown previously. And it only belongs when L is equal to 0. Then you will have when and that L will be equal to the orbital quantum number. And you know that when L is equal to 1, the values of ML will be equal to 0 and plus minus 1. When L is equal to 0, that is orbital quantum number L is equal to 0, then the orbital magnetic quantum number will have three values. One value is 0, the other two values are plus minus 1. This is also shown over here. And you know that I have applied the magnetic field to an atom, which is shown by the Z direction. So when ML is equal to 0, that is the orbital magnetic quantum number is 0, then the loop is perpendicular, then the loop orientation is shown against ML is equal to 0. And the vector L is perpendicular to the vector B. So when ML is equal to plus 1, then the orientation is shown against over here. This is the current loop of the electron. And the direction of the L are shown when the orbital magnetic quantum number is equal to plus 1. Similarly, when M is equal to minus 1 as shown by the green color, then the loop is shown in green and the orbital angular momentum is shown in green. So all these angular momenta will start precessional motion about the Z direction or about the magnetic field. And these are the current loops that I have shown. These current loops, in the current loops, you know that when you apply the external magnetic field, these current loops will start precessional motion, or in principle, the orbital angular momentum of the electron will start its precessional motion about the magnetic field B. So let me explain this diagram further. The orientation of L is not random in space. The orientation of L is random in space only when the magnetic field is not present. So if you are not applying any magnetic field to atom, then the orientation of the orbital angular momentum in an atom is completely random. That is, the direction of L is not quantized. But when you apply the magnetic field, the direction of L is quantized with respect to the magnetic field. But when the magnetic field is not present, then L is quantized in the sense that it is perpendicular to the current loop of the electron. In that sense, you can say that when the magnetic field is not present, then the direction of L is only known by the direction of the current loop. So the L vector will be perpendicular to the direction of the current loop. So the orientation of L is not random in space. When one axis is established by the external magnetic field, a component of L, which we regard as LZ component, gets quantized. That is, it has a fixed magnitude and also it has a fixed direction. This is the meaning of quantization. Due to quantization, only one discrete value of alpha, that is the angle between B and L, will be allowed. So only one angle of alpha will be allowed. And then the vector L will have its magnitude, which is represented by Lz, can be measured, which we record as the Lz component. The component of L in the Z direction is Lz is equal to ml into h bar. So this is what we can find out the value of the projection of the angular momentum vector L in the Z direction, which is given by Lz. It is equal to the orbital magnetic quantum number ml multiplied by h bar, where ml will have the following values: 0, plus minus 1, plus minus 2, plus minus 3, and so on. The maximum value of which is equal to ml plus minus L. So the maximum value of ml will be equal to plus minus L, and it will start its initial value from ml is equal to 0. So you see that if you choose L is equal to 1, quantum number this L. So you see that if you choose this L is equal to 1, then only three values will be possible for ml. ml will be equal to 0 and plus minus 1. And corresponding to these three values, I have shown these three current loops. Corresponding to ml is equal to 0, corresponding to ml is equal to plus 1, and corresponding to ml is equal to minus 1. These three current loops have been shown corresponding to three values of the orbital magnetic quantum number ml. The orbital quantum number L is related to the magnitude of the orbital angular momentum L as given by. So you see that this is a relationship that relates the quantum numbers on the right hand side with the angular momentum on the left hand side. So on the left hand side, you have the magnitude of the angular momentum of the electron or the atom, and on the right hand side, you have the square root of the orbital quantum number L multiplied by L plus 1 multiplied by h bar outside the square root. So on the right hand side, the quantity L is actually the quantum number, and on the left hand side, the quantity which is L mod is actually the magnitude of the angular momentum. The largest possible component of L in the Z direction, that is Lz maximum, has a value equal to LH bar, because the maximum value of ml is equal to L. So the maximum value of Lz, if you want to calculate the maximum value of Lz given by equation number 24, then you would need to replace ml by its maximum value, which is equal to plus minus L. So in equation number 26, you have the maximum value of the Lz component, which is equal to L times h bar. So I have taken only positive sign over here to show the positive magnitude. As L is quantized, so mu L is also quantized, which means that mu L has a fixed value of component along the Z direction, and it has a fixed direction with respect to the magnetic field. So this is the meaning of quantization. That is, the direction is fixed with respect to the magnetic field, and the magnitude is also fixed with respect to the magnitude with respect to the applied magnetic field. This is the meaning of quantization of these both quantities. That is the quantization of the orbital angular momentum and the quantization of the orbital magnetic moment of the electron or the atom. For its component in the Z direction, the quantization rule is over here. And this is what we are following, equation number 12.15a, that mu L is equal to minus E over 2m naught into L vector. And if you take the Z component, you need to take the Z component on both sides. And then we don't have the vectorial form, but we have the scalar form, because we are now going to calculate the Z vector along Z vector of this equation along the direction of the magnetic field. So you can write that mu Lz is equal to, you can multiply with h bar and you can divide with h bar, so that you can introduce Bohr magneton, which is equal to h, which is equal to E h bar over 2 m naught. You can replace this quantity by mu b, and the rest of the quantity is Lz over h bar. This Lz is nothing but ml, magnetic quantum, orbital magnetic quantum number, that you can take from previous equation. That is, from this equation, you can take the value of ml is equal to Lz over h bar. So I have introduced the value of ml over here and rearranged it as minus ml into mu b. So the maximum value of mu Lz max is equal to minus the maximum value of ml times mu b. Now there are two possibilities, ml is equal to plus L or ml is equal to minus L, because the maximum value of ml is plus minus L. So two answers are minus L into mu b or plus L into mu b. Or simply you can write that the maximum value of mu Lz, that is the maximum value of the z component of the orbital angular of the orbital magnetic moment of the electron or the atom, is equal to L times mu b, where mu b is the Bohr magneton. The energy of interaction between the magnetic moment mu L and the magnetic field B has three components, out of which only Z component can be observed. And the other two components, X component and Y component, that is mu L X component and mu L Y components, are averaged out during the motion of the electron in the form of the current loop. So only the Z component is measurable. So you see that today I have discussed in much greater detail the orbital angular momentum of the electron and its quantization, and I have also discussed the quantization of the orbital angle of the orbital magnetic moment of the electron or the atom. And I have also related these quantities with each other, and I have shown that these two quantities will precess about the direction of the magnetic field of the magnetic field applied externally to the atoms. I have also discussed the quantization of the Z components of these two quantities, and I have also discussed that their X components and Y components will average out during the motion of the electron. So you see that this lecture, that is, you know that in this lecture we wanted to discuss these terms, that is the orbital and spin magnetism. I have discussed only the orbital magnetism over here. The spin magnetism is yet to be discussed. So spin orbit coupling, that you know that I have not discussed spin yet. So when the spin angular momentum and the spin magnetic moment will be discussed, and the presence of this spin in the presence of the, and the spin of the electron in the presence of the magnetic, in the presence of the external magnetic field will also be discussed. Then we shall also discuss the spin orbit coupling. And when the spin orbit coupling will be discussed, then the fine structure will also be explained very well there. We shall also be discussing in this lecture the orbital angular momentum and the orbital magnetic moment, which I have discussed. I have also discussed the magnetic moment and their precession in the applied magnetic field. In the next lecture, I shall be discussing spin angular momentum, spin magnetic moment, spin quantum number, what will happen to the spin angular momentum and the spin magnetic moment in the presence of the external magnetic field. And then I shall also be discussing the interaction between the orbital and the spin magnetic moment in the next lectures. And then on the basis of these interactions, I shall be explaining the fine structure in much greater detail. So this lecture is continued So this lecture is continued to the next slide. But however, for the time being, this lecture will continue. But for the time being, I am ending this lecture and it will continue to the next lecture also. So this is the end of slide number 12A of the course on atomic and molecular physics.